is Dr. Kuldeep Saha from IISER Bhopal. He will talk about embedding 3 manifolds in 5 manifolds using OpenBook. Okay, I request Kuldeep to start.
Yeah. Thanks to Shoma for introducing. So I will talk about embedding 3 manifolds in 5 manifolds using OpenBook decompositions. So let us quickly recall what an embedding is. So an embedding of a manifold M inside a higher dimensional manifold N is just an injective regular immersion. So now the first major result in embedding theory was given by Whitney, who showed that every n manifold can be smoothly embedded inside R2n, which is the Euclidean space of dimension 2n. And this was also an optimal result in a sense because there are many examples. For example, RP2 does not embed inside R3. And later Hirsch showed that if you take orientable closed 3 manifolds, by Whitney they embed in R6, then he showed that they can also be embedded inside R5. So a proper embedding is an analog of embedding for manifolds with boundary. So for example, here proper embedding from V del V to W del W is an embedding such that the restriction of the map F naught on the boundary of V goes into the boundary of W. So here is an example where a genus 1 surface with 3 boundary component is properly embedded inside the 3 ball. And we also note that the boundary of this surface should meet the boundary of D3, which is S2, transversely. So this should not be tangent to the boundary S2 of D3. So now what is an open book decomposition? So open book decomposition of a manifold is essentially a way to decompose the manifold in simpler parts. So in particular, if you start with a closed oriented manifold M, then the decomposition consists of a codimension 2 oriented closed submanifold B with a trivial normal bundle in M. That means the normal bundle is isomorphic to B cross D2. And if you remove B from M, the complement fibers over S1, where the closure of the fiber is called page, and the boundary of the fiber of the closure of fiber is our manifold B, which is called the binding. So here is an example. If you take the manifold S2, the 2 sphere, and remove the north and south pole from it, and take the closure of the remaining part. So to take closure, you have to compactify it by attaching 2 copies of circles, one near north pole, one near south pole. Then it is just a cylinder, so which is just a trivial line bundle over S1. So fibers are 0-1 intervals. So here is another nicer way to see what an open book. So all the n thetas for where theta lies in S1, all the fibers are actually homeomorphic. So assume that they are homeomorphic to some sigma. So then the total space of the open book M can be written as the union of 2 parts. One part is a mapping torus of sigma with some diffeomorphism of sigma. That is the return map of this fibration pi. And the other part is boundary of sigma, which is just binding B cross D2. So note that phi is a diffeomorphism of sigma relative to boundary. That means near boundary it is identity. So the boundary of mapping torus is just sigma cross boundary sigma cross S1. And also this part has boundary sigma cross S1, del sigma cross S1. So along boundary, we can attach them by identity map and we can recover the whole space M. So here is a schematic of what an open book looks like. It exactly looks like an open book. So in particular, this description says that an open book is uniquely determined by its page sigma and monodromy phi. So, and we denote an open book with this notation AOB sigma phi. So Sn has an open book decomposition with page n-1 disk and monodromy identity. So Sn is the n-dimensional sphere, unit sphere inside Rn plus 1. So we also recall what is a Dehn twist. So a Dehn twist is just a homeomorphism of an annulus relative to the boundary, and it is characterized by what it does to this arc joining the 2 boundary components. It sends this arc to this arc, and if you want to know the precise map, here it is. So we already seen by the previous example of Sn that S3 has an open book decomposition with disk page D2 and monodromy identity, but S3 can also be given another open book decomposition where the page is DT star S1. So DT star S1 denotes the unit disk cotangent bundle of Sn, and DT star S1 is actually homeomorphic to an annulus, and monodromy is this Den twist on the annulus. And in higher dimension, we have one more example. S2 cross S3 has an open book decomposition with page, the cotangent bundle of S2 and monodromy identity. So now, once we have defined what is an open book decomposition, there should be an equivalence that when two open books are same. So two open books, sigma 1 phi 1 and sigma 2 phi 2 AOB, they are same if there exists a diffeomorphism H that takes sigma 1 to sigma 2 and such that this diagram commutes. So in particular, what this says is that if you take an open book sigma with monodromy phi, page sigma and monodromy phi, and if you conjugate the monodromy with a diffeomorphism of sigma, say psi, then the total space of the open book doesn't change. And also note that the isotopy class of phi uniquely determines the total space M of the open book up to diffeomorphism. So next we come to the notion of embedding for open book decompositions. So we say Mn open book embeds inside V capital N if there exists an open book AOB sigma M phi M for M and another open book AOB sigma V phi B for B such that there exists a proper embedding of sigma M inside sigma B and this commutativity relation holds. So all this relation is saying that if you embed sigma M inside sigma B and then apply sigma phi B, it restricts to phi M on the embedded page. So a straightforward example is that Sn with page Dn-1 and identity monodromy open book embeds inside S capital N with page D capital N-1 and identity monodromy. Capital N is greater than N, small n. So the question here we ask is that does there exist a fixed open book of dimension 5 where all open books of a closed tree manifold admit open book embedding? So this was the initial question, and then we answered that yes, it happens. And in fact, we could show that we could show two such 5-dimensional manifolds. So one is S2 cross S3, which is the boundary of S2 cross D4. So which is a 4-disk bundle over S2. And there exists another 4-disk bundle over S2, which is called the twisted 4-disk bundle over S2. And it has boundary, which is denoted by this twisted product of S2 and S3. So for S2 cross S3, you can take as page any disk bundle over S2, which has Euler number even. And for this twisted bundle, you can take as page any disk bundle over S2, which has Euler number odd. And in both cases, you take monodromy as identity. So how to go about the proof? I will talk about the outline. So the main thing is that what is known as flexible embedding. So a flexible embedding of V inside W. So now everything is in proper setting. Boundary goes to boundary. So V embeds inside W flexibly if any diffeomorphism of V can be induced by an isotopy of W. So that is what these conditions are saying. So in particular, note that a flexible embedding of V inside W implies proper embedding of the mapping torus of V with any diffeomorphism psi inside mapping torus of W with monodromy identity, and which in turn implies open book embedding of AOB V psi inside AOB W identity. So showing flexible embedding is enough. So now the starting point is the following. First, we want to show that there exists a flexible proper embedding of an annulus inside the 4-disk D4. And to find that, we observe that this lemma, what this says is that you can embed an annulus inside S3 in such a way such that there exists a isotopy of S3, say which goes from time 0 to time 1, such that its time 1 map induces a Den twist on that embedded annulus. Okay. So, and to see this is very easy because we already saw that S3 has an open book decomposition whose page is homeomorphic copy of an annulus, DT star S1, and monodromy is Den twist. So how this says this lemma, because so this is the DT star S1. So this is an embedding of annulus. It is not isotopic to the annulus, standard embedding of annulus itself. This is called Hopf annulus, and it is a cipher surface of this Hopf link. And this cutout part we say Hopf band. So if you take this Hopf annulus as your embedding of annulus, then this lies as page inside your mapping torus of the open book. And in the S1 direction of the mapping torus, if you go for time 1, you start from a page and then you go around and come back, it induces one single dent twist. If you go say k many times, it will induce kth power of dent twist. And similarly in the other direction, if you go, you can induce the negative powers. And we know that the mapping class group of annulus is generated by a dent twist. So that means that this isotopy gives us a kind of flexible embedding of this annulus inside S3. And using this, we can show this that there exists a proper flexible embedding of the annulus inside D4 and D4. So now, so before that we define one more thing, DM. So this is the disk bundle over S2 with Euler number M. And now what we want to do is we want to embed any surface sigma. We want to find a proper embedding inside DM such that any simple closed curve on F sigma should be isotopic to some curve which has a tubular neighborhood that is homeomorphic to that looks like that is isotopic to Hopf annulus neighborhood. Because once a neighborhood looks like Hopf annulus neighborhood, then you can use corollary 10 to induce the dent twist on that curve, along that curve. Okay, so that's the idea. So what we do, so we need a description of DM as handle body. So DM can be obtained by attaching a two handle. So a two handle is just this thing, D2 cross D2. And it is written in this fashion because the attaching region is del D2 cross D2, which is just a solid torus. And the attaching map is a map from S1 cross D2 to S1 cross D2. So here S1 may be knotted like this. And if you take a point on the boundary of D2, it may not go parallelly. It may go like, it may link the core circle multiple times. And if it links it M times, we say that the framing of handle attachment is M. So one can see that DM can be obtained from D4 by attaching a two handle along the unknot on the boundary of D4, that is S3, with framing M. Okay. So please note, if you attach a two handle along some knot here in case here it is unknot, then this unknot is going to bound a disk, which is the core disk, that is D2 cross 0. Okay, the origin of D2 cross 0. That disk is bound by this knot here. So now we can proceed with the proof. So DM contains D4 because it is obtained by attaching 200 to D4. And so take a tubular, a collar neighborhood of the boundary of D4. So it looks like S3 cross minus 1, 1, where S3 cross 1 is the actual boundary. So now what do? We embed a disk inside the 0 level, that is S3 cross 0. You attach a Hopf band. Okay, so now initially it was one boundary component, you have created two boundary components. Push these two boundary components at the level S3 cross S1. So by pushing, I mean take the boundary components and take the product 0 to 1, 0, 1 interval, and that is cylindrical region here. And then attach a two handle along one of the two boundary components. So for example, say we attach here along the boundary component H1. So what it will do, it will create the one extra boundary component, and this will give a new embedding of our disk inside DEM. So what is the benefit of this local model? The benefit is the following. So if you start with this arc inside disk alpha naught, then what you can do, you can isotope this arc along the cylinder and then take it over the core disk of your two handle and then land it on this arc alpha 1. So note that here alpha naught has a standard boundary neighborhood, but here we can isotope it to another curve which has a twisted neighborhood that looks like a Hopf annulus neighborhood. So this is the main idea, and disk is nothing special here. It works for any surface with boundary, and in general the picture looks like the following. Say if you have a surface with n boundary components, attach a Hopf band to one of the boundary components. So you have increased the boundary component number by 1. And so what you do, you again push these two boundary components to the boundary of D4 and attach two handle along one of the boundary components. Okay, and what it will do is the following. If you take any simple closed curve C on your surface, okay, you can isotope it near CH. So CH is a curve that passes through this twisted region of Hopf band. Then using this disk, you can isotope C to the connected sum of C with CH. So given any simple closed curve C, we can isotope it to a curve which has Hopf annulus neighborhood, because this contains the twisted region. And that is what we wanted initially. So that's the idea. And actually this technique gives us a new proof of Hirsch theorem, because if you take M equal to 1, and if you can manage the embedding, flexible embedding to be disjoint from the zero section of D1, then it gives a new proof of Hirsch theorem. That's all. Thank you.
Okay. Any question? Okay, let's thank the speaker. Okay.